So, hello everyone. I'm Swati. I work at Samsung in the Solution Product Engineering Group. The topic of my presentation is navigating NVMe-Fabric authentication, best practices for key management in pre-AV and post-AV environments. So here is the agenda. First, I'll cover NVMe-Fabric authentication basics, basically where in-band authentication sits in the connect flow and the basic authentication terminology. Next, I'll walk through DH-HMAC-CHAP authentication. This is the in-band protocol used today by NVMe-Fabrics. Then we'll look at few security threats. After that, we'll compare single key versus multiple key models and how they affect security and operations. Finally, I'll share our experiments and observations and conclude. So this talk is a continuation of our last year talk. Last year at SDC, we gave a talk on evaluating the discovery system, discovery automation introduced recently in NVMe on a large-scale NVMe-Fabrics deployment. Basically, in that session, we shared our experience in deploying automated discovery using NVMe STAS in a highly scaled NVMe-Fabrics environment. We shared how automated discovery behaved at scale, the operational pain points we hit, and lessons from our testing. So this year, basically, we worked on the discovery automation, and we added authentication on top of it. And in this talk, I'll share our experience and the challenges we faced while adding authentication with automated discovery. So before we dive deeper, I'll go through some of the basic terminology of NVMe-Fabrics authentication. We all know the Fabrics protocol. Basically, it extends NVMe across a network fabric. It could be a TCP transport or a RDMA. So hosts can access NVMe devices as if they were local. So today, NVMe-Fabrics supports two types of authentication methods. The first one is in-band authentication with DH-HMAC-CHAP, and the second one is secure channel with TLS on NVMe TCP. In this talk, we'll primarily focus on in-band authentication with DH-HMAC-CHAP. So few in-band authentication basics. So in in-band authentication, the authentication itself happens inside the NVMe-Fabrics connection setup. There is no separate control plane. The protocol used is based on a challenge-response model. One side issues a challenge, and the other side proves its identity by computing the right response. So both sides basically use something called a key, and the keys are never sent on the wire. The authentication types that in-band authentication today supports are unidirectional and bidirectional. Bidirectional is basically mutual authentication. We will talk in detail in the upcoming slide. In unidirectional authentication, the subsystem primarily, here in this talk, I'll be using subsystem, controller, and target like synonymously. So I'll be using these terms interchangeably. So in unidirectional authentication, in terms of NVMe-Fabrics, the subsystem authenticates the host. And in bidirectional authentication, once the subsystem has authenticated the host will again authenticate the subsystem as well. So some of the key terms that I'll be using in this talk are like the basic NVMe authentication concepts. The first thing is like entities. So basically, the NVMe host or the subsystem are the NVMe endpoints or the entities that have to be authenticated. The second terminology is keys. Each NVMe entity will use a key to prove its identity. So I'll be using terms like KH and KS. KH will be the host key, and KS is the subsystem key. So each entity stores only its own key, and it uses the key to prove its identity. Again, the keys themselves, they never are transmitted over the wire. So with this basic understanding, we can walk through the authentication flow. Yeah. I hope this is visible. So as I mentioned before, in this talk, we'll focus on NVMe-Fabrics in-band authentication, and we'll take the case of an NVMe-Fabrics protocol on TCP transport. So let's start with the basic bring up between a host and a controller for in-band authentication. We firstly begin by establishing a TCP connection. Yeah, it's a TCP session. This is simply a transport connection establishment on the NVMe fabrics so that the two entities, NVMe entities, the host and the controller are the NVMe entities, can communicate. So at this point, nothing NVMe specific is done yet. It's the fabric transport initialization step. At this point, only the transport is initialized and the TCP session is created. Next, the host issues a connect command. The connect command is primarily used in NVMe Fabrics protocol to create the queues, and after the connect command is successfully established, the NVMe commands will start flowing in the protocol. So the prerequisite in this entire configuration for authentication is that both the host and the controller should be provisioned with authentication. So if any of the parties are provisioned with authentication, in the connect response, the controller responds with I think I'm hurrying up. So the host will send a connect command, and if the authentication is set up, in the connect response, the controller responds with authentication required. It sets a flag called auth request, which basically means authentication is required. And it places the connection in an authentication required state. So until the authentication completes, the controller accepts only connect and authentication related commands. No fabrics, IO commands are allowed at this point. So any other commands like fabric commands or NVMe admin commands or IO commands will be not processed. Only they'll be returned with an invalid status. Only authentication related commands are allowed at this point. So next is the authentication transaction. This transaction is performed on the same NVMe session, that transport connection that we have formed. So it uses the authentication send and receive commands to exchange protocol messages for the selected in-band authentication method, which we will talk in detail in the next slide. So the purpose here is, in this authentication transaction, is the verification of the entities. Basically, both the entities have to identify that they are the valid entities for this connection. So the connection remains in authentication required state until this transaction completes successfully. Yeah. So once this transaction is completed, now the connect command response will be success, and the queues will be set up, and the subsequent operations, NVMe operations, can begin. Basically, we can it essentially creates a admin queue, usable admin queue, and the host also creates a IO submission completion queue and begins issuing normal NVMe commands. So in summary, in the flow, the first step is the transport connection is established, and then the connect command and connect response is sent. If authentication is set up, an additional authentication transaction phase is done, and if this authentication is successful, the NVMe queues are set up, and subsequently all the commands can flow. NVMe commands can flow over the connection. So next I'll talk about the DH-HMAC-CHAP in-band authentication. So NVMe Fabrics in specification 2.0, Fabric specification 2.0 introduced DH-HMAC-CHAP for in-band authentication. So DH-HMAC-CHAP is a key-based authentication protocol that is based on CHAP. We used to have CHAP earlier in iSCSI protocol. So CHAP is basically a challenge handshake authentication protocol. CHAP is enhanced in DH-HMAC-CHAP to use hashed message authentication code HMAC mechanism, which comes with a stronger hash function. And it also optionally adds a Diffie-Hellman exchange, DH exchange, further to enhance the security by preventing eavesdropping attacks. So basically it adds an additional key exchange on top of the HMAC. In order to authenticate, both the parties, your host and the controller, uses their own DH-HMAC key that is associated with the entity's NQN. So we all know that in NVMe protocol, NVMe-Fabrics protocol, both the sides, host and controller, have to have their own NQNs. So the key has to be associated with the NQN. And when the primary goal of this entire transaction is that if a host is associated with a DH-HMAC key to its NQN, it has to prove that it is the right key. So DH-HMAC key itself is derived from a secret that is a simply ASCII string value which the administrator can configure. Each host or the controller or the subsystem will transform the secret by applying a hash function, taking as inputs the secret, the NQN along with some context, NVMe related context, and which results in the key. So this ensures that the resulting key is uniquely tied to each NQN. So what I'm trying to say is the administrator will initially configure something called a secret, which is a plain ASCII text. So DH-HMAC-CHAP uses strong security. So this secret will be converted to a key using applying a HMAC on the secret and tying it up with the NQN of the entity with some other NVMe Fabric related context. So DH-HMAC-CHAP, since it works on in-band authentication, it supports both bidirectional and unidirectional authentication between a host and a controller. So I'll go through the figure now. So if you see these messages, I'm not sure if it's visible. There are like multiple phases. The first phase is auth negotiate. In the authentication negotiate phase, which we saw earlier in this diagram, this is the authentication transaction phase. So we are actually expanding on it. So in the auth negotiate phase, host will send couple of parameters. The most important ones are the transaction ID, the authentication ID, like what protocol we will use to authenticate this entire transaction. So auth ID will be essentially DH-HMAC-CHAP because that's the one currently defined in the spec. If tomorrow a new mechanism is added, then it'll have like variants. Currently it is DH-HMAC-CHAP, and it will also share the list of hash IDs that it has, which the target or the controller can choose from, and the DH group ID list also. So all these parameters are basically negotiated before the entire challenge response protocol is done. So first I'll cover the unidirection exchange. So in the unidirection exchange, as I said, the key is never transmitted on the wire. So the host will have its own KH key, and the controller will have its own KC key. So host needs to primarily prove that the key that it has is valid, and the controller has to prove that the key it has is valid. So the first, once the parameters are negotiated, the controller will create a challenge, and based on the negotiated parameters, and it will send it to the host. This is the challenge C1 that the controller will create. Once the challenge is sent to the host will use its own KH, the HMAC-CHAP key that is configured with, and it will create a response R1. This response R1 will be validated by the controller, because the controller will also be provisioned with the KH key. So the party which is verifying the keys has to know the key of the entity that it is verifying. So host will be provisioned with its own KH key, and the controller will also know the KH key. It will use the KH key to create this to check this response. So if the response matches, the unidirection authentication is completed, and the controller will send a success message. Now, if we have provisioned this entire communication to be of bidirectional nature, then the controller will also when the controller is sending a success message, it will also send a R2. This R2 is in response to the C2, the challenge which host will send if bidirectional authentication is provisioned. So when unidirectional authentication is completed, the host, if bidirectional authentication is configured, host will create a challenge and send to the controller using the controller's key. The host should be now provisioned with the controller's key. It will use that key and it will create a challenge. And the controller will now use its own key to create a response. And if this response is the one which is with the host, the entire transaction is successful. So in summary, these are the 4 phases. The auth negotiate, where all the parameters are negotiated. The challenge, as I said, it's a challenge response protocol. So whichever entity is trying to validate or authenticate the other entity has to create a challenge. In unidirection, the controller will create a challenge using the parameters that were negotiated, and the host will reply with the correct response. And internally, which is not shown here, the controller will go and check this R1 by calculating the R1 based on the host key that it is keeping. And in mutual verification, same thing is repeated at the host side. So now that we have seen the in-band authentication flow, let's discuss some of the threats that it is designed to withstand. In the next set of slides, we will see some network-related security threats. We do have some other kind of threats, like where the threats where the stored media itself is stolen, right? Those kind of threats we are not tackling here. We are only tackling the threats which are related to the network, where the attacker can go and attack the network. So DH-HMAC-CHAP or in-band authentication protects against that. So we'll see how in-band authentication protects against those threats. Yeah. So I'll start with passive eavesdropping. This is the simplest kind of threat. The attacker just sits quietly on the network and listens. They don't change or inject anything. They only capture messages going back and forth, hoping to figure out keys or save the traffic for later. So if you see, this is a host and a subsystem or controller which is connected on NVMe-oF TCP, and it's a passive listener. It's just listening on this connection. So the host, let's see step by step what happens. The host starts an NVMe-oF connection over TCP. The controller or subsystem replies. Meanwhile, the passive listener is sitting on the path, copying everything flowing over the wire. So what exactly can this listener see during the DH-HMAC-CHAP process? They only see two things: the public DH-HMAC-CHAP related values, the non-secret numbers, the challenge exchange, to help both the sides generate a shared key session, right, that we saw earlier. The challenge part it can see. It can also see the HMAC outputs, basically all the authentication tags created from challenges and all the context. But what it can't see is the host key and the controller key, because they are never transmitted over the wire. The host key KH and the controller key KC are never sent across the wire. Instead, the protocol uses the challenge response setup, where only the challenges and responses are sent on the wire. So since it can't see the long-term keys, it won't help the attacker. Seeing the DH public values doesn't actually help, because you would still need the private part of the private exponents or the private equations to compute the shared result. Seeing the HMAC tags which are transmitted on the wire also doesn't help, because HMACs are one way. Without the actual key, you can't make a valid tag or a new challenge or a new session. So bottom line is, a passive eavesdropper learns nothing useful. They might record all the traffic, but they cannot pretend to be use it in any way to attack the network. So now that we have covered passive listening, let's move on to active attacks, where the attacker actually tries to reuse or tamper with messages, starting with the next attack, which is replay. So a replay is simple. An attacker captures an authentication message from an earlier connection. So think of an old R1. We saw R1, right? The response when we are doing this challenge response protocol, there will be a response generated which shows the success. So the attacker will reuse all this information to create a new session. It will start a session B between the host and the controller. Down at the bottom, you see the controller subsystem explicitly expects a fresh challenge response for this new session. So every time a new session is created, right, all the challenge and responses are newly calculated. So even if it has captured the previous challenges and responses, they are not useful in the new session. Basically, all the messages and IDs are valid only for the previous captured session. Each run uses its own identifiers and per run values. So everything is basically temporary, and it's based on it's related to that particular session. The controller binds its verification to the session's context. So anything copied from a different session is out of the context. So this results in HMAC calculation mismatches. For every new session, the parties, since the parties are using new Diffie-Hellman values and DH-HMAC context, this attack is not useful. Basically, DH-HMAC solves it. So in summary, all the messages and IDs are valid only for that session, even if the attacker creates a new session, right? If it uses the previous values, the HMAC calculated will mismatch, and this attack is prevented by DH-HMAC-CHAP. So the next attack is man in the middle. This is when an attacker wedges in between the host and the controller. This is the man in the middle attack. They can relay the traffic, they can try to alter the messages, try to downgrade the entire negotiation. For example, pushing the connection toward a weaker hash or a weaker DH group during auth negotiation. During auth negotiation, both the host and controller negotiates on all the parameters, right? So this attacker will try to reduce the parameters that are exchanged. So In this kind of an attack, basically, how DH-HMAC solves this kind of an attack is why this fails with DH-HMAC-CHAP is because the HMAC is computed over the IDs and the Diffie-Hellman values, the random values that are generated are ephemeral. They are only relevant to the session that is used. So those bind the run to exactly what the two entities negotiated. If the attacker changes anything, like the IDs or the DH group value or the negotiated parameters, the verifier's HMAC recomputation won't match the transaction, won't match, and what the controller is expecting, and the transaction will fail. If the attacker only relays without changes, they still can't create valid responses because they don't know the long-term keys, the host key and the controller key. So they can't complete successfully any of these steps. So basically what we are trying to say here is that DH-HMAC-CHAP resists any kind of tampering or downgrade attempts done by the attacker.
That's true, but it only affects the authentication transaction. It doesn't affect the data afterwards, right?
Yes, yes.
Okay. You may need to repeat that because I think the recording is...
Okay. Actually, secure channel is the best way to protect against man in the middle. But man in the middle is not typically explained in the spec, but the inherent property of the DH-HMAC protocol is such that it will at least safeguard the authentication session. Yeah.
No, the authentication transaction.
Transaction, yeah. Next is the impersonation. Yeah. This is the one we will be actually discussing in this talk. So this is basically very simple. An attacker pretends to be a valid entity. It pretends to be either a valid host or a valid target to access without owning the key, to get an access to the other entity without owning the key. So on top of the picture, we have a legitimate host that holds its key KH1. At the bottom, we have a controller which verifies responses using the valid key. Onto the right side, we have an attacker trying to pretend that it is H1 and talk to the controller over as if it is a legitimate host H1. So how DH-HMAC protects against it? The controller issues a challenge. A valid host must compute a correct DH-HMAC-CHAP over the challenge and all the context using the right KH1 key. The controller recomputes the expected HMAC with its KH1 verifier and compares. The attacker doesn't have this KH1, the authentication key for the host. So since it doesn't have the right key, the entire computation to create the valid HMAC, right, it fails. So unless it can somehow get possession of these key, the impersonation will pass, which we will talk later. But typically in an impersonation scenario, the attacker will try to pretend that it is H1, and the way to do it is get possession of this key, the legitimate key of the host. Or if it is attacking a subsystem, it will try to get access to this key of the controller. So, so up to now, we talked about how in-band authentication works on the wire. From here, I'll describe all the security challenges specifically how we provision and manage keys for hosts and subsystems, and how those choices affect risk. We will start with the simplest model and then examine what happens if something goes wrong. So, yeah. So as I said, DH-HMAC-CHAP is the authentication inbound authentication protocol for NVMe. Today, DH-HMAC-CHAP supports two types of models: single key per entity and multiple keys per entity. That means if you have consider this is a network fabrics where you have n number of hosts and n number of subsystems connected to each other. In a single key model, each entity will have one single key belonging to that entity. So host H1 will be provisioned with KH1, host H2 will be provisioned with KH2. So this is the computation key it uses for creating the response for the challenge response protocol. And the subsystem, let's take the case of unidirectional authentication where the target is authenticating the host. So in unidirectional authentication, the subsystem, since it has to authenticate the host, it will have its own computation key. If at all it has to respond for a bidirectional authentication, it has to be configured with its own computation key, and it will also have all the host verification keys. So these host verification keys are nothing but the keys of each of the hosts. So if host H1 is provisioned with KH1, subsystem S1 will have KH1 and also the NQN of this host, right? And since it's single key per entity, all the hosts are configured with one unique key, and the subsystem, since it has to verify all these hosts, it will have this list of all the host keys mapped to their NQNs, right? The same way, subsystem 2 also will have its computation key, which will be used in bidirectional authentication and all the host verification keys. Yeah.
During setup, how do you establish the common key?
How do you establish the?
Yeah, how do you set up the common key between them? Common key, the common secret, the KH-bank, they all have the same key. How did you store the same key into the subsystem and the host?
So in NVMe, today we have NVMe CLI, which generates this key based on the NQN. So you can create the key unique to, it's an admin step basically. You have to go to the host and create the key and pass that key. This is out of the spec, so you have to pass that key to that subsystem. That same key has to be stored in the subsystem for verification.
Do you assume that the key is generated within the subsystem that you're entering it into, or are you assuming that the key can be created on some device elsewhere and then some through some transfer?
Yes.
But that transfer is subject to the vulnerabilities.
Yeah. So this is an admin provisioning step. So say I have 4 hosts. In all the hosts, I'll go and create a key, its own key. And today we have NVMe CLI. It will create a DH-HMAC compliant key. Now this key has to be provisioned in the subsystem. So provisioned means it is not going through the protocol. It has to be, an admin guy should know this host key, and it should be provisioned. The same key should be provisioned in the subsystem.
So there are several different key management systems. Some are commercially available, some are public domain. Is any of that covered even notionally within the standard, or is that?
No. Today the standard doesn't define it. Am I right? Yeah. Yeah,
ABE, which I think she's going to talk about.
Yeah. So the objective of this slide is single key per entity. So in a typical NVMe fabrics, we'll have multiple hosts and multiple subsystems. And what we are trying to show is like every entity has its own unique key. And the verification entity, if subsystem is verifying a host, it has to store all the keys of all the hosts. right? Yeah, and it works in the same way. When host is authenticating the subsystem, the host will store all the keys of all the subsystems, which is not shown in this diagram. So what is the security challenge in a single key? So consider a case where this subsystem N is compromised. So if this subsystem N is compromised in single key, since it has the list of all the host keys, right? Now, assume an attacker has attacked this subsystem. Say H1 is an attacker or H-1 is an attacker. Now it can pretend to be any of these hosts, right? Because it has the right key. So this I'll show in experimental results also. So in summary, if any of the subsystems is compromised, the attacker can impersonate any of the hosts to any of the subsystems. So what is happening here is the entire network, all the subsystems are impacted. The entire network is kind of impacted. So there is a security vulnerability. So in summary, attacker can impersonate any host to all the subsystems, leak of any of the keys, right? Leads to the attacker impersonating any host to any subsystem. Now, in multiple keys, DH-HMAC-CHAP also supports multiple keys. In multiple keys, we have, again, it's a network fabric. We have multiple hosts and multiple subsystems. We are, again, taking the case of unidirection, where a subsystem is authenticating the host. So the host will be having a list of keys, but now the keys are mapped based on per subsystem. So if the host has to talk to subsystem 1, it will have a KH1S1. It is a per pair mapping, so KH1S2 for subsystem S2, right? So same, in the subsystem side, subsystem will have its computation key. Say its subsystem is supporting only unidirection and single key per entity model. So subsystem will only have a KS1. If it is supporting multiple key per entity, again the subsystem will also have a KS1, H1, KS1, H2, that entire list. For simplicity, I have not shown that. So what happens if an attacker comes and attacks SN? So even if SN is compromised, the attacker will only gain access to the keys that SN has, and SN will have only the keys of every host which are pertaining for that subsystem, right? So every host, as I said, will have a KH1S1, host 2 will have a KH2S1, so on. So if this subsystem is compromised, attacker will gain access to all the host keys relevant to only this subsystem, right? So the attack basically doesn't compromise the other subsystems. If the attacker tries to access another subsystem, the same host key will not work because this system requires the host key which is mapped to this subsystem, right? So in summary, attacker can impersonate any host to only the compromised subsystem, right? Attacker can, since he has access to all these keys, it can impersonate any of the hosts to only the compromised subsystem. The leak of the keys basically doesn't affect any other subsystem. So the entire network is not compromised. The other part is the scaling part. So up till now, we have looked into the security challenge. Next, I'll talk about the operational issues. So The goal of this entire invent authentication is that it should happen at scale. Entire authentication process should happen at scale. So in this section, I'll be talking about the scaling challenges. Even if the security is good, the way we provision and manage keys can make or break a deployment. So I will use some diagrams to explain that. Yeah. So in this diagram, I'm showing the scaling challenge. I think it is very much self-explanatory. So I'm taking the case of multiple keys per entity, where each entity is mapped with multiple keys. So each host uses a different key per subsystem. So host H1 has a key for subsystem S1 and a separate key for subsystem S2 that we discussed. So on the subsystem side also, each subsystem maintains verification keys for each of the hosts with the NQN. So this is a lot of information to be maintained. So what happens when we try to scale? So if we have N subsystems and M hosts, while this design requires N into M distinct keys. On addition of any of one single entity, if you are adding, say, a new host or a new subsystem, right, to this configuration, these many times the provisioning will be impacted. So on addition of a new entity, each entity needs to be re-provisioned with its own key. So there is a lot of provisioning that we are doing here. So if you have to onboard a new new host, say H3 or something, we must generate all these keys, right, and provision all the subsystems with the new keys related to this new host. Same goes with the subsystem. If you are adding a new subsystem, all the hosts have to be provisioned with the keys which are relevant to this subsystems. So this entire scaling part is like, it's a scaling issue basically. It's a M into N provisioning problem. So, the theory that I explained, we also tried it in our with our storage solution in our lab. So, as you were asking, right, how the keys are generated. Today, the font is small. I hope it's visible. So, NVMe-CLI supports this DH-CHAP generation parameter. Basically, you can create a DH-HMAC key using gen DH-CHAP key, and you can provide the length of the key also, like what length of the key you want. And this is a standard format which is defined in the spec. Here, like after the colon, this part that you see is the secret, and this is the HMAC that is applied on this secret, and based on that the key is generated. So we tried the security vulnerability of the single key. First you connect a host which is provisioned with a HMAC key which is provisioned for that particular host, is the right key for that host, and you send a NVMe connect command. So this is the syntax for sending a connect command over TCP. You have to share the DH-HMAC secret that was generated using the CLI, and you can see the devices connected. Now, to show the impersonation, we have tried doing the same thing over a new host, where we are taking the same key, and we are also, since we are impersonating the host, we use the host1 NQN, and the connection goes through, which is not expected.
Should be expected.
I mean, in impersonation, somehow the attacker has gained access to this key. That's what I'm trying to show here.
But you've got the same identity, you've got the same host NQN, and you've got the same key. It should be expected.
Okay. Yeah, I mean, it is a success, but yeah, we are trying to show that impersonation, how it will work. It should be expected. I've put unexpected because the scenario we are showing, it's an attack. Somehow the attacker has gained access to this key, since the spec doesn't define how to protect these keys. The second experiment is we tried single key and multiple key deployments with both manual discovery and automated discovery. So what we saw is in the single key model worked consistently, like if we use NVMe CLI to do manual discovery. Today, both the NVMe target and discovery automation uses something called NVMe stas. So manual discovery and automated discovery, they both support single key, and the automated discovery with authentication was successful. When we tried multiple keys, we saw certain challenges. Basically, in Linux kernel target, today only single key provisioning is supported, and the CLI does support sending multiple keys, but there is all the keys have to be provisioned by the admin. There is no mechanism to remember these keys. So it's the current support in the kernel target is mainly for the single key. The host side does support multiple keys, but since the kernel target doesn't support it, we saw authentication was not going through. Same thing we tried on automated discovery, NVMe stas, and in automated discovery also, we found that when we configure multiple keys, so say this is our setup where we have a target having multiple subsystems configured with multiple keys, and there is this host which is provisioned with which is configured with automated discovery. It is able to discover only the first subsystem. The rest of the subsystems it's not able to connect to. So basically, the multiple key per entity support is still not completely there. We were talking to the maintainers, and we have passed this request. So to solve all this, we have just 5 minutes remaining. So recently in the specification, AV is introduced. So AV is a centralized authentication verification entity. We are next planning to evaluate AV. You have a question? Yeah. As a possible path to simplify all these operations. So what AV does, AV is recently introduced in the NVMe specification. So what is AV? AV is a centralized, you can consider it as a database which stores all these keys. So it's an outsourcing of the verification process through a secure centralized entity. AV itself runs on top of TLS, so it's secure, and it stores basically all the verification keys. So since AV is storing all the verification keys mapped to the corresponding NQNs, both the subsystem and the host, right, they only need to store their computation keys. The verification keys are no more needed to be provisioned at both the ends. So this is how the same DH-HMAC-CHAP flow that we had seen earlier works when AV is introduced. The I'll just go through it fast. So we know that it's a challenge response protocol. When AV is introduced, the only thing that is changing the protocol, if you see, remains the same. The verification of the keys, if it is a unidirection authentication, the controller verifies the host. Here, the verification of this key will be done by the AVE. And if the AV is behind, configured at the host side, though it's a centralized entity, it can be configured either at a controller side or a host side. In this figure, we are showing that it is configured at the controller side. So all the responses that the controller was creating, now the AV will be calculating, and the protocol itself doesn't changes. Basically, the challenge response verification, the AV will be doing. So our findings is basically, to sum it up, pre-AV, if we are using single key, it's not secure, and we did speak to some of the maintainers, and the suggestion is that we should migrate to AV. For multiple keys, though it is secure, we have this scaling provisioning issue. With AV, the entire network is secure. No scaling issues also, because AV will do the entire provisioning part. And AV works on top of single keys. Multiple keys are not required. So in conclusion, these are the takeaways. Yeah. A single key in conclusion, basically, we talked about primarily single key per entity, which has a security vulnerability. And if one of the entity is compromised, right, the entire network is compromised. And multiple key per entity, it's a per pair keys, and the security blast radius, right, it will be reduced, but it has a provisioning overhead. And AV centralizes the entire verification process. Now the endpoints or the entities only keep their own verification keys, and it enables per pair semantics at scale. That's all. Thank you.